Okay, I think we'll get started. If you're coming from the GNL project, I encourage you to look at the introductory video to this playlist to make sure this is the right series for you. Otherwise, we're going to talk about uniform circular motion and in particular the forces involved in that. We've already seen that for circular motion, we need an inward acceleration in order to change the velocity vector. So we're still going to be talking about very special motion where the speed going round in a circle stays the same. So the length of the velocity vector is not changing, but the direction is changing as it goes around the circle. That's referred to as uniform circular motion. And the velocity vector is always tangent to the circle. So if this circle is representing the position, so anywhere on this circle is the object is at that particular point, then the object is moving with velocity v tangent to that circle. And then normal to the circle pointing inward is the velocity vector, or sorry, acceleration vector, the acceleration vector. And that's referred to as centripetal acceleration. And we've already derived the formula, but we'll write it here again, that the magnitude of the acceleration is proportional to the, or given to us by the velocity squared over the radius. So if we have a nice tight circle, we have more acceleration because we have to change that velocity vector in a shorter region of space. If we have a long swooping curve, then their acceleration needs to be less. Likewise, if we're going faster, then we're changing that vector faster because we're moving around that curve faster. And it just, as we saw earlier, it turns out to be proportional to the speed squared. Now, let's characterize this motion a little bit. This motion is repetitive, right? So we start here, we come back to here, we just keep cycling. So one of the ways to characterize that motion is how long does it take to get from one point back to that same point again. Doesn't matter what point it is, that will always be the same. So any point we choose on the circle, how long does it take to come all the way back around? And that's called a period. And unfortunately, we use the symbol capital T, which we're using for tension as well. And there'll definitely be some problems where tension appears and period appears. So you have to be a little careful with this notation. So that's the time to complete one revolution. If we take the reciprocal of that, what we're asking is how many revolutions occur in 1 unit of time, like 1 second. The SI unit of that is using the second. So how many cycles per second, and that's called a hertz. And it's given to us, or we use the symbol Hz. So it's one of the few SI symbols that has 2 letters. Okay. Let's now use just some geometry of circles and think about how we could characterize this velocity. Well, the circumference of a circle is 2 pi r, right? And then the time it takes to get around is 1 period. So this is a distance, this is a time, so that's our velocity to get around the circle, the velocity we're going to get around the circle in time t. And then since this is 1 over t, that's frequency. So missing an r here. 2 pi r times the frequency is our speed. Then we can plug this back into this formula, and we get an acceleration of 4 pi r frequency squared. So this is getting squared. So the 2 is squared, that's the 4. The pi is squared. The r is squared, but then there's an r down here, so that will cancel. And so we just get r to the first power, and then the frequency is squared. And, another mistake here. We can substitute back in for period if we want. And so then we'd have 1 over t squared here down here. Okay. So with this, I think you can practice a few problems, pretty simple algebra here to solve for one or the other given the other two, working in period and frequency as well. Well, if there's an acceleration, we know there's a force by Newton's law, F equals ma, Newton's second law. and that force is in the same direction as the acceleration. So this force must be directed inward. So this is going to always be directed inward. And so as our velocity is tangent to the circle, then we experience a force curving us inward, right? We know from Newton's first law, if we're undergoing uniform motion and there's no forces acting on us, we will continue to go in uniform motion. Well, we're not here. We're not in uniform motion. We're changing, and we are doing so because of this force. Okay, so a little careful here back with this name. This is uniform circular motion. It means the speed is not changing, but it doesn't mean the velocity is not changing. Since this is called centripetal acceleration, then this force associated with it is called centripetal force. We can substitute in for the acceleration. So acceleration over here is just mass times velocity squared over r, always directed inward. Let's do a quick example. Let's say we're holding on to a toy plane that's got some kind of engine and it's stuck to a rope here. The rope is 15 meters and the plane is moving at 55 meters per second, and it's a little bit less than a kilogram, so 0.75 kilograms. Well, we can calculate the force as being the mass, so mass times the velocity squared, so 55 squared over 15. You can check my arithmetic there. I got 157 newtons. Let's try a little bit different problem that might not feel like exactly this setup, but it is. So let's imagine that we're chasing on the gym floor in our socks, and we know that if we take a corner too hard, we'll wipe out, we'll slip out. And what that happens because there's not a lot of friction between our socks and the gym floor. So in order to make a turn on the gym floor, we have to be pushing against the floor to provide that centripetal force. And that's provided by the friction. If we have shoes on and the gym floor is nice and clean, we have a lot of friction, so we can push off very easily and make a sharp turn. If we're running in socks and we don't have as much friction, then we can't make quite as sharp a turn, or if we need to make a sharp turn, we have to slow down more than if we're in shoes. So let's take an example here where we have a static friction coefficient of 0.22, and we're trying to make a 3-meter radius turn. So we're chasing in the gym, we're trying to make a 3-meter turn. If we consider ourselves right here, here's our free body diagram. We had a centripetal force pushing us inward. The nature of that force, the only thing that's pushing us inward is our feet against the floor, and that's given to us by our friction. So let's write the formula for the frictional force, and the magnitude here is going to be the normal force, mg, times the static friction coefficient, and then the vector component, meaning going directed inward towards the circle of that motion. Force from over here, we have our formula there, so we can combine these two. The static friction is providing the centripetal force, so we can equate these two. And notice the mass cancels. So whether it's me running or you running or anybody with a different mass, doesn't matter. It's mass independent, this answer. It's only going to depend on the coefficient of static friction and the speed to determine how whether you'll wipe out or not. So we have mu g equals v squared over r. We can solve for v squared and then take the square root. And so we get this. Plugging this in, we get 2.5 meters per second. So you can, again, check my arithmetic there. Now, let's talk about a related force. It's different than a centripetal force because it's what's called an apparent force. The centripetal force is a real force. This is an apparent force. It's called the centrifugal force, and it's really the reaction force to the centripetal force. So if we have by the third law, we know that for every force, there's an equal and opposite force on a different free body diagram. So let's imagine this. Let's say we have this little bucket and there's a mass in here. If we start to spin this bucket, this mass is going to move to the outside of that bucket. So if we were just had a camera inside the bucket, it would appear the mass is moving towards the outermost part of this bucket, so that it ends up against the back of the bucket. So it would appear that there's a force pushing the object outward, and that's referred to as centrifugal force. Now, what's really happening here is the mass is just wanting to stay in uniform motion by the first law, but then the bucket comes into play, right? The bucket comes into play and starts wanting to push the velocity vector around for this mass. So the bucket here, the back end of that bucket, is providing the centripetal force this way. Well, the reaction force then, this mass is providing a force this way. And so that the motion of this object towards the outer edge of that bucket is given rise because of this centrifugal force. And you're probably most familiar with that if you've done any kind of biochemistry or even some biology where you're using a centrifuge to spin out, say, a sample of cells, and the heavy stuff goes to the bottom of the test tube and the lighter stuff goes to the top. You stick the test tubes in something that spins really quickly, and we get that centrifugal force pushing everything to the outside, and the denser objects get pushed out more aggressively, and so you can layer out components of a biological mixture with a centrifuge. So we take advantage of that in the centrifuge, of this centrifugal force in a centrifuge. Okay, so not a whole lot today. Formulas are pretty simple, so just get some practice with this. We will start to look at some equations of motion for circular motion as well, and we'll start to see an analog or a comparison between linear motion and circular motion. We just get a hint of it here in the name, uniform circular motion. So we have a circular version of our uniform motion in one dimension.